Imagine this for a second. You're driving your car, you see a reason to slow down, you hit the brakes, but instead of stopping, the car speeds up. You're pressing the brake pedal to the floor, but the engine is roaring and you are no longer in control. This isn't some scene from a movie, it was a terrifying reality for people. And the real story here isn't about what you can see, like stuck pedals or floor mats. Nope. It's about a hidden flaw, buried deep inside millions of lines of computer code. So let's get into it. This is the story of how one tragic accident uncovered a hidden world of digital danger.
Okay, so let's set the scene. It's September 2007, a clear day in Oklahoma. Jean Bokout is behind the wheel of her 2005 Toyota Camry, and her friend Barbara Schwartz is riding in the passenger seat. As she's taking an off-ramp, something goes terribly wrong. She loses control of the throttle, and the car just starts accelerating, completely on its own. Now, this is the part that turns this from a tragic accident into a really profound mystery. It's the physical evidence left right there on the pavement. 150 feet of dark black skid marks. This was not a case of a driver panicking and stomping on the gas instead of the brake. No way. The evidence was literally burned into the asphalt. Jean Bokout was fighting that car with everything she had. She was standing on the brakes. And you can bet that this one piece of evidence became the absolute cornerstone of the legal battle that came next. As the plaintiff's attorney, Graham Esdale, put it, Toyota simply couldn't explain those skid marks away. They were undeniable proof that the driver was doing one thing, and the car? Well, the car was doing the exact opposite.
So how is that even possible? How can a car accelerate when the driver is desperately, with all their might, trying to make it stop? This is where the whole investigation started to peel back the layers on a problem that was way more complex than anyone imagined. Let's just walk through the sequence here, because it's terrifying. First, she loses throttle control. The car starts picking up speed. Then, the normal brakes, they can't overcome the power of the engine. So, in a last-ditch effort, she pulls the emergency brake, and that's what creates those long skid marks. But even that wasn't enough. The car crashes into an embankment. Tragically, Barbara Schwartz was killed, and Jean Bokout was severely injured. Every single thing a driver is taught to do in an emergency, it all failed. With all the obvious mechanical explanations just not adding up, investigators knew they had to look somewhere else entirely. They had to go beyond the engine, beyond the brakes, and pry open the car's electronic brain. You know, for a long time, the easy answers for unintended acceleration were things like misplaced floor mats, jamming the pedal, or sticky gas pedals. But cases like this one, with clear, hard evidence of braking, that pointed to something much, much deeper. The focus had to shift from the hardware you can touch to the software you can't see, to the millions of lines of code running the whole show. So, to crack this digital code, literally, the legal team brought in the big guns. We're talking Michael Barr, a top expert in the kind of software that runs inside, well, everything, and Philip Koopman, a professor from Carnegie Mellon who specializes in systems where failure is not an option. And Barr's mission was just monumental. For over 20 months, think about that, almost 2 years, he sat in a locked, secure room, just combing through Toyota's source code, line by painstaking line. And what he and Koopman found inside that code was, to put it mildly, an absolute disaster. The technical term they used for it, well, it paints a pretty vivid picture. They called it spaghetti code, and it's exactly what it sounds like. It's a term programmers use for code that is so tangled, so interconnected, so convoluted that it's nearly impossible to follow. Imagine a giant bowl of spaghetti, where you try to pull on one single noodle and the entire bowl comes with it. That's what they were looking at. Trying to fix one tiny problem could unpredictably create a dozen new ones somewhere else. And here's where it goes from being just messy to being downright deadly. Michael Barr described Toyota's safety architecture as a house of cards. Just one little puff of wind, one small failure, and the whole thing comes tumbling down. He discovered that it was entirely possible for the very systems designed to prevent a disaster, the fail-safes, to be shut down at the exact same moment the throttle went rogue. And get this wasn't just some outsider's hot take. The investigation dug up an internal document where one of Toyota's very own programmers called the code spaghetti-like. They knew. Inside the company, on some level, they were aware that their code was a dangerously complex mess. Okay, so calling the code a mess is one thing, but the experts uncovered specific, shocking numbers that revealed just how bad the problems really were.
Just look at this number for a second. 81,514. What on earth could that possibly be? That's the number of times Toyota's code broke the rules, specifically a set of mandatory safety standards for programming called MISRA. Think of it like the building code for a house, but for software. There's an industry rule of thumb that says for about every 30 of these violations, you can expect one major bug. So, do the math. This code wasn't just a little non-compliant. It was statistically guaranteed to be filled with thousands of potentially catastrophic bugs.
All right, here's another number that just floored the experts and later the jury. Over 10,000. That's how many global variables were in the code. Now, a global variable is basically a piece of data that any part of the software can change at any time. It makes the system completely unpredictable. For safety-critical systems, things you don't want to fail, the industry best practice standard for global variables is 0. None. Nada. Toyota had over 10,000. As one expert testified, 10,000, no, we're done. It is not safe.
And the problems just kept piling up. The system had what are called single-point failures. That's like flying a plane with only one engine and no backup. One little glitch could bring the whole thing down. They found that critical software tasks, including throttle control, could literally just die. Just stop running. And the system wouldn't even notice. Why? Because the watchdogs software that was supposed to spot these failures was itself broken. Oh, and the cherry on top? No peer code review, which is a basic, fundamental practice where programmers check each other's work.
But maybe the most damning piece of evidence of all was this internal Toyota email. And look at the date, September 2007, the very same month as the Bokout crash. It says, fail-safe is not part of the Toyota's engineering division's DNA. Continuing on as is would not be a good thing. This wasn't just a bug or a mistake. This was a deep, recognized cultural problem with their entire approach to safety. So, what are the wider consequences here? How could a problem this massive stay buried for so long? And, more importantly, what does it mean for the rest of us?
Well, the problem basically hid in plain sight because it was just so complex. Government regulators didn't have the software engineers on staff to even know what to look for. Even a prior investigation by NASA was seriously handicapped. They had limited time, they didn't get access to all the source code, and, as testimony later revealed, they were misled by the company about some of the car's safety features.
When the jury in the Bokout case finally heard all of this evidence, their conclusion was swift, and it was brutal. They found that Toyota had acted with reckless disregard. That phrase is a very big deal in the legal world. It was so severe, in fact, that Toyota settled the case just hours later to prevent the jury from moving on to the next phase, awarding punitive damages, which would have likely been absolutely massive. And this all brings us to the final, really critical question that this whole story leaves us with. Because this was never just about one car company or one accident. We are living in a world that is completely run by software. The code isn't just in our cars, it's in our phones, it's in our hospitals, it's in our homes. And as this story proves, when that code fails, the consequences can be devastating. So it really makes you wonder, who is checking the work?